All right, welcome on in. Good to see you. Lesson 2.1, Simplify Radicals. Okay, so first of all, we want to take a look at what are the parts of a radical. Okay, this little n on the outside is known as the index. This tells us how many groups to put them into before they can come out of the radical. The bar itself is called the radical. Okay, and then the number on the inside is called the radicand. Okay, now if you don't see a number outside here as the index, then you've always got to assume that it is a 2, and that's known as a square root. Okay, so if you don't see a number out there, we just assume that it's a 2, and that's also known as a square root. Okay, now we want to look for perfect squares that the radicand is divisible by, and that'll help us break these down. Is that the only way to work these? No, but that's one way to work them out. Okay, so we're going to look at that next. So these are perfect squares. Okay, so if I had a radical 1, that is a perfect square, which comes out as a 1. Okay, if I had a radical 4, that's a perfect square that comes out as a 2. Okay, a 9 is a perfect square that comes out as a 3, so on and so forth. And what I mean by that is if I have like radical 9, that is the same thing as saying radical 3 times radical 3. Well, since there's 2 radical 3's there, okay, since there's 2 here, they come out as a 3. So radical 9 is the exact same thing as saying 3. Okay, that's where we get them as perfect squares. Okay, 121 is a perfect square that's 11, so on and so forth. Okay, we'll refer back to this list here in a minute. Okay, so our directions on our first few problems say to factor out by using a perfect square. Well, if I look at 75, I know that 75 can be factored out as radical 5 times radical 25. Well, if I look, radical 25 is a perfect square. Look back here. See, radical 25 is right here. It's a perfect square, so it comes out as a 5. So I know radical 25 can be broken down into radical 5 and radical 5. Okay, those two, because it's a perfect square, come out as a 5. This radical 5 here is all by itself. There's just one of them, so it has to stay in the radical as a radicand. Okay? Well, for 40, I know, can be broken up into 4, radical 4, and radical 10. Well, look, radical 4 is a perfect square. Okay, what we mean by that is that it can be broken up into radical 2 and radical 2, okay, which means it's a perfect square. 10 gets broken up into radical 2 and radical 5. And if I look here, this perfect square, those, since there's a pair of them, there's 2 of them, the 2 comes out. These 2 here, the radical 2 and radical 5, they're by themselves, they have to stay in, so we just multiply them back together again. Okay? Okay, 128. So if we take a look at that, radical 128, well, first, let's take a look at our perfect squares. Nope, it's here between 11 and 12, so it's not a perfect square. Okay, so what I can do is take it, I notice that it's even, so I just divide it by 2. So I know that radical 2 and radical 64. Oh, look here, 64 is a perfect square. That is radical 8 by radical 8. Okay, I can now go back and see, oh, there's 2 radical 8's. They come out as an 8. The 2 is left over, so it's got to stay in. Once I break these numbers down, like that 64 I broke down into radical 8 and radical 8, it's now gone. The 128 I broke down into radical 2 and radical 64, it's now gone as well. Okay? All right, radical 10. Oh, look, radical 10 is a perfect square. That's the same thing as a radical 100. I'm sorry. It's the same thing as radical 10 times radical 10. That number's gone. Look, since I've got 2 radical 10's here, Okay, it just comes out as a 10. Nothing's left over. 10 is my answer. All right, I want you to give these two a shot, or give 72 a shot on your own, because the next one's a little bit different. Give 72 a shot on your own, pause it, and then come on back. All right, now with 72, I notice it's not a perfect square, but I look and see it's even. So I know that radical 2 will go into it, and that's radical 36 times radical 2. Oh, look, 36 is a perfect square. That's radical 6 times radical 6. It's a perfect square, so now I'm all done. Okay, 6 can come out, radical 6s can come out as a radical 6. This radical 2 is all by itself, so it's got to stay in. And there's my solution. Okay, now with this next one, it's a little bit different because I got that 4 on the outside. Do the same thing. I noticed that 2 times 100. Radical 2 times a radical 100. Oh, look at this. Radical 100 is a perfect square. Radical 10 and radical 10. Okay, it's a perfect square. So since it's a perfect square, that 10 comes out. This 2 is all by itself, so it's got to stay in. But now I cannot forget about this 4. This 4 and this 10 are both on the outside, so let me do this instead. This 4 comes on the outside, and I multiply it by that 10. Since the 10 came out, it multiplies by. So 4 times 10 is 40, and then my radical 2. Okay? So if the number's on the outside, when I bring a number out, we multiply them together. Negatives don't make any difference. They're the exact same things. Okay? So they don't change anything. So 27, I break that down into, well, it's not even, but I know 3 goes into it. So radical 3 to radical 9. Oh, look, radical 9, perfect square. That's radical 3 by radical 3. It's a perfect square. So this 3 comes out. The negative 2 I've got to drop. Times this 3 that comes out. That's gone, that's gone. That stays inside. So that's negative 6 radical 3. And what I mean by stays inside is it stays eradicated. Okay? 64. Oh, you might have noticed right away that 64 is a perfect square of radical 8 times radical 8. So since they're perfect squares, okay, these two will come out as an 8. Oh, there's nothing left over, but don't forget to bring that negative down. Boom, so it's negative 8. Okay? All right, now those are perfect squares, so now we've got perfect cubes. And what this means is that if I've got a perfect cube, like the cube root of 8, that's a perfect cube, which comes out as a 2. Cube root of 27, that's a perfect cube, which comes out as a 3. What that means is if I use the cube root of 27, and this is a cubed root because it shows that 3 is the index, it's called a cube. If I do the 27, look what happens. Cube root of 3, or 3, oops, 9, and then it goes 3 and 3, and these are all cubes here. Okay, see what happens is that 9, that 27 are gone. See how I've got 3 of them here? All 3 of those come out. So cube root of 27 is equal to just 3. Now instead of putting them in groups of 2, I got to put them in groups of 3. And I put them in groups of 3 because of that index. Okay? So if I take a look at 81, all right? 81, well, let's look back here. Is it? Nope, it is not a perfect cube root. So with 81, I look and see, oh, 3 goes into that. So I got the cube root of 3 times what? Well, that is going to be a cube root of 27. So 27 I know is a cubed root. So 81 is now gone. So now I do 27. So 27 is cube root of 3 times cube root of 9. And then 9 is cubed root of 3 and cubed root of 3. Okay? 27 is gone, and now the 9 is gone as well. Now I put them in groups of 3. We said 27 was a perfect cube, and it is right here. Those 3 come out as a 3. cubed root. Now, notice I've got this 3 left over. It stays in as the radicand. Okay, so when I notice this 27 is a perfect cubed root, I just don't even have to break it down like I did here in orange. You can just pull it out as a 3. Okay, I just broke it down for your visual. Okay, 64, same thing. Well, oh, look at this. 64 is a cubed root of 4. So I know that 64 is just going to come out as 4. Okay, but let's see how it works. Let's see how it works. Well, I know 4 goes in here. 4 times the cube root of 16. And then 16, that's 64, is now gone. Breaks down into a cube root of 4 times a cubed root of 4. And now 16 is gone. Okay? Once again, you notice the 64 is a cube root of 4. You can just put down 4. I'm just showing you here so that you can get a visual of there's where my 3 4s come, so my answer is just 4. Okay? All right. I want you to pause the video, give these 2 a shot on your own, then we'll check them together. All right, well, I'm going to do this very first one. I may do it a little bit different way, but I'm going to notice that this 40, the first thing I notice is 4 and 10. Okay, because of the 0 tells me 10. So I know I could break it into 2 smaller numbers. So that 40 is now gone. Okay, now this 4 can break down into a cube root of 2 times a cube root of 2. It's now gone. Well, the 10 breaks down into a cube root of 2 times a cube root of 5. The 10 is now gone. Okay, and if I look here, look, I've got 3 cube root of 2's, which means that 2 comes out. This lonely little 5 has to stay in as a cube of 5. Okay, you might have broken it up into 2 times 20 and then broken it up that way. Perfectly fine. It all works. It all works. Okay, all right. This 500, I'm going to notice that it goes into a cube root of 5 times a cube root of 100. 500 now gone. The way you do these is you just work out what you notice. Now, I noticed that the 100, okay, is a cube root of 10 times a cube root of 10. That makes 100. 100 is now gone. Okay, now the 10 breaks down into a cube root of 2 times a cube root of 5 on both of them. Okay, I'm running out of space here, guys. Oops, sorry about that. Cube root of 2... cube root of 5. Well, now I've got all kinds of numbers written down here. These 2 10s are gone. So what I end up doing is I just take these cubes and I just drop them all down. Okay? Oops. So I go cube root of 5, that one. Then I go cube root of 2. And then I go cube root of 5. And then I go cube root of 2. And then I go cube root of 5 again. Okay? Now, it's just looking at, do I have groups of 3? Well, I sure do. I've got 1, 2, 3. Those 5s come out. I've got 2 cube root of 2's, which means cube root 2 times 2 is 4. So this whole problem here ends up becoming 5 cube root of 4. Okay, as I break it on down. We kind of look at these as trees, and these little things here are berries, and the berries fall off of the tree, and then we can kind of combine them when they're down at the bottom. Okay. All right, last one's here. We got the number on the outside, so what do you think you're going to have to do to that? Yeah, you're right. You're right. Whatever comes out is going to multiply by it. So I noticed that 16 is a cube root of 2 times a cube root of 8. That makes 16. 16's gone. Now 2 is prime. I'll leave it alone. So the 8, I know, is a cube root of 2 and a cube root of 4. So the 8's now gone. And then the 4 is a, is a cube root of 2 and a cube root of 2. Now I look back. Do I have groupings of 3? I sure do. 1, 2, 3. Here's one grouping. Those 2's can come out. My 5, okay, my 5 here's got to drop down as well. And then my cube root of my last 2, this one here, stays inside. So what's this equal? 10, cubed root of 2. 10 cubed root of 2. Okay? And the very last one, done the exact same way. Just don't forget to multiply that 2 in there. So I take here and I know that there's this cubed root of 5 times the cubed root of 27. Ooh, 27 is a perfect cube, isn't it? Yes, 27 comes out as 9, or 3, sorry, comes out as 3. How do I know? Well, here, I'll go ahead and show it for you. This comes down as a cube root of 3 times the cube root of 9. Oops. Then the 9 gets broken down into a cube root of 3 by a cube root of 3. 9 is now gone. Okay, and if I look, see here, here's my 3 cube root of 3's. So that means it comes out as a 3. Don't forget your 2 down here. And then don't forget your lone leaf radicand of 5, which stays inside. 3 times 2 is 6 with cube root of 5. Okay? And there's working with simplifying radicals down to their simplest form.